Well, hello, my friends. And you know today is going to be a great day because we get to learn more about chemistry. So, we are moving on to our next lesson in our theme involving electron structure and chemical reactivity. This lesson will focus on intermolecular forces and how the forces between molecules contribute to physical properties of compounds. Okay, so the first thing that we're going to talk about is a review of what an intermolecular force is. So inter means between and molecular, obviously molecules. So we're talking about covalently bonded compounds here. So intermolecular forces determines the physical properties of a substance, such as volatility, which means willingness to evaporate, solubility, and conductivity, among others. Others such as melting point and boiling point, density, strength, can all be determined by intermolecular forces. So there are four main types of intermolecular forces that you guys will be responsible for knowing. The first three types are kind of a catch-all term for them. It's called van der Waals forces. These are all forces between molecules that do not involve electrostatic attractions between ions or bond formation. So what I mean by that is if we have an ionic compound, those are obviously electrostatic attractions between ions. If we have forces that are between partial positive and partial negative charges between different molecules, those are van der Waals forces. Those include things like London dispersion forces, dipole-dipole, and dipole-induced dipole. And a very specific type of dipole-dipole that is often kind of separated from van der Waals forces because it's a little bit stronger is called hydrogen bonding. We're going to go over that first, but the definition of hydrogen bonding is when we have a molecule that has hydrogen covalently bonded to a very electronegative atom, specifically nitrogen, oxygen, or fluorine. This hydrogen is attracted to a lone pair of electrons on a neighboring electronegative atom. Specifically, it has to be nitrogen, oxygen, or fluorine. So we're going to go over hydrogen bonding first. Okay, so here is a diagram so you can kind of see what I'm talking about. It is the strongest form of intermolecular attraction. So that means boiling points are significantly higher than those you would predict for other elements in that column, or if you have elements of similar molar masses. So, for example, we have molecule 1, it contains hydrogen, and you see that it is covalently bonded to a very electronegative atom A here. And in this example, A has to be nitrogen, oxygen, or fluorine. Then it is attracted to a lone pair on molecule 2. We'll put that as just molecule B. It can be the same molecule, just a lot of them. So this can also be A, but again, these have to be nitrogen, oxygen, or fluorine. And then this electronegative atom, again, is covalently bonded to something else. It does not necessarily have to be hydrogen, which is why it is labeled C here. Okay, so we have this hydrogen, again, covalently bonded. And this electronegative atom, because it's more electronegative, it has a partial negative charge on it, which means it is sharing electrons in this covalent bond, but the electrons are spending a little bit more time around this electronegative atom compared to the hydrogen, which causes the hydrogen to have a partial positive charge. If that hydrogen comes near another molecule with a nitrogen, oxygen, or fluorine, those are electronegative enough to have a partial negative charge that is then attracted to this partial positive charge on hydrogen. The reason it could only be NO and F is because those atoms have strong enough electronegativities to pull the electrons in that covalent bond away enough to form this difference in charges that create a hydrogen bond. So looking at water, for example, you can see the dashed line represents the hydrogen bond. Remember, a solid line is a covalent bond, not a hydrogen bond. You represent the hydrogen bonds, again, with these dashed lines, and you see the hydrogen, which is attracted to this lone pair on a neighboring water molecule. It does not necessarily have to be between all of the same molecule. For example, we have water mixed with ammonia here, and you can see that because hydrogen is covalently bonded to nitrogen on this one, these hydrogens can form hydrogen bonds with a neighboring ammonia molecule or a neighboring water molecule. Likewise, this hydrogen can form a hydrogen bond with neighboring water or ammonia molecules because they are electronegative enough to form these hydrogen bonds. And remember, the bonds within these molecules are going to be polar covalent because there is a net dipole towards the more electronegative atom. So, graphically speaking, why is boiling point for molecules containing hydrogen bonds higher than others in the same group? Okay, so for example, looking at group 16, okay, group 16 is this red line right here. So, this is the one that contains oxygen on the top of the group, and then going down the group are different atoms, ending with tellurium down here. If you have hydrogen covalently bonded to group 16 atoms, you might predict that the boiling point would increase going down. And that is because we have more of what we call London dispersion forces as we go down a group. We're going to get to that a little bit later. But normally, boiling point trends tend to increase going down a group. However, you can see that water here with the oxygen covalently bound to it, because of the hydrogen bonding, it has an abnormally high boiling point than you might predict. According to the trend, it should be down here, but it's not. It's the highest one. So this trend occurs with also fluorine and nitrogen groups. So group 17 and group 15, because again, these three are electronegative enough to break that trend. However, carbon is not electronegative enough. So you see it does follow its predicted pattern for group 14, where carbon covalently bonded to hydrogen has the lowest boiling point of the group. And then going down the group, it has higher boiling points. So you can also look at some organic compounds here. The one on the left does not contain hydrogen bonds because there is no hydrogen covalently bonded to oxygen, whereas ethanol on the right does. Even though they have very similar molar masses, so they're similar sizes, the ethanol forms hydrogen bonds, whereas the methoxymethane over here on the left does not. So you can see the great difference in boiling points between them. Methoxymethane actually has a negative boiling point, so it's usually in the gaseous state, whereas the boiling point of ethanol is 79 degrees Celsius, so it is a liquid at room temperature. So again, these intermolecular forces not only determine things like boiling point, but states of matter as well. All right, so the next type of intermolecular force we're going to talk about is dipole-dipole attraction. So one of these, dipole-dipole attractions are classified as one of the van der Waals types of attractions. So these are attractions between opposite partial charges on neighboring molecules. However, this is different than a hydrogen bond because the electronegative atom that causes a partial negative charge is not strong enough to form a hydrogen bond. So any other electronegative atom that can be attracted to an electropositive atom can form a dipole-dipole attraction. Remember, hydrogen bonds are special. They have to be either nitrogen, oxygen, or fluorine. Any other atom is going to cause a dipole-dipole attraction. So the strength of these are going to vary depending on the distance between the molecules as well as the orientation of the dipoles. So generally, these are going to be stronger than the London dispersion forces, which is the weakest type of intermolecular force. So the strongest is hydrogen bonding, then dipole-dipole, then dipole-induced dipole, and lastly, London dispersion. So these melting or boiling points are usually higher than in nonpolar substances that do not contain dipoles, which makes sense. An example here would be hydrogen bromide. You can see that bromine has a partial negative charge here, again, because it is more electronegative than hydrogen. So this does cause a dipole in the molecule, just not strong enough to be considered a hydrogen bond. And both of these molecules have permanent dipoles. That means that there's always going to be a difference in electronegativity between the two atoms strong enough to cause this dipole. So you can see here, a nonpolar molecule that does not have an overall dipole has a much lower boiling point, this is in Kelvin by the way, compared to something that does have a permanent dipole. So dipole-dipole attractions can only occur in polar molecules. So you see here the difference is 229 Kelvin versus 249 Kelvin in the one with the dipole bonds, dipole-dipole bonds. Sorry, and also I apologize if I say bonds when I mean intermolecular forces. It's kind of a nuance, but intermolecular forces are not bonds, okay? So bonds are only characterized by intramolecular forces or interatomic forces like ionic, covalent, metallic. Anything else is not technically a bond. Some people call them intermolecular bonding. That's okay, but I rather call them a force, so intermolecular forces. Okay, so the next type of van der Waals force is a dipole-induced dipole. This happens when a molecule with a permanent dipole interacts with something that's nonpolar, gets close enough to it to induce a temporary dipole in that nonpolar molecule. So basically what this means is you have something polar, for example, hydrogen bromide here. This bromine is more electronegative. So if it gets near something nonpolar like helium, the electrons in helium do not want to be near that negative dipole because they repel. So for a instantaneous moment, the electrons will move to the opposite side of the helium atom to be away from that negative bromine right here. So you can see here that there is a temporary dipole put in this nonpolar molecule. It only lasts for a second, and in that second, that hydrogen bromide can be attracted to that helium. Larger molecules are more susceptible to this than smaller ones, and that's because in a larger molecule, those electrons are more mobile. They're not held as tightly to the nucleus as opposed to smaller molecules. So, for example, if we're looking at diatomic bromine, that's going to be much bigger than helium. So the ability of hydrogen bromide to induce a dipole in bromine is a little bit larger than it is able to do so in helium. Again, these are very temporary. They're not very strong, and they are definitely weaker than dipole-dipole bonds and much weaker than hydrogen bonds. All right, last but not least, London dispersion forces. This is what occurs between nonpolar molecules. So again, kind of like dipole-induced dipole, except this time it occurs between two molecules that are both nonpolar. Okay, so basically what this means is at any one moment in time, the electrons might not be exactly evenly distributed in the nonpolar molecule. They don't last more than an instant. It's just kind of like dipole-induced dipole. It's just if something is temporarily out of balance in the electron cloud, it can get near something that is nonpolar and induce a temporary dipole in that other nonpolar molecule. These are the only types of intermolecular attractions that occur in nonpolar molecules. And because they are so weak, only lasting an instant, because again, it just happens based on the random electron distribution in these molecules, they generally have really low melting and boiling points, and it also explains why nonpolar substances are often gases at room temperature. So again, the reason that boiling points tend to get lower for nonmetals down a group, that's because they're bigger. They have more electron density. So there's more of a chance that some of the electrons can be more towards one side of the atom than the other, just due to probabilities of how the electrons are moving and because there are more electrons. So therefore, bromine, diatomic bromine, has stronger London dispersion forces than something like diatomic fluorine, which is much smaller. I hope that makes sense. Okay, here's another picture of London dispersion forces. You see, normally it has symmetrical distribution if it's nonpolar. However, at a certain moment in time, maybe that distribution is unsymmetrical. And so when that happens, an instantaneous dipole occurs on that nonpolar molecule. It gets near something else that's nonpolar, causes a dipole in that other molecule, and they have a London dispersion force, a very instantaneous attraction between them because of the movement of the electrons to one side of the atom. Again, both of these are nonpolar. This only happens instantaneously. It is not permanent. Okay, so looking again at the halogens, you can see here the trend in this London dispersion forces. Fluorine has the lowest boiling point, whereas iodine has the highest. Also, it makes sense why fluorine's a gas and then chlorine's a gas, bromine is a liquid because it's larger, and then iodine is a solid because it is the largest of the halogens. If you're ever asked to name the forces that occur between compounds, London dispersion should always be listed, regardless if there are additional forces present. There can be a combination. Polar molecules will always have London dispersion present, even if they are polar. Okay, so I know that's confusing, but polar molecules have electrons moving around, right? Isn't there going to be a probability that randomly some electrons are going to be more on one side than another? Of course. So London dispersion exists in all molecules. And you can see that the larger a nonpolar molecule is, the higher the boiling point. Even though it's still low technically compared to other things, it's higher because the longer a nonpolar molecule is, the more electrons there are and the more probability they have that they can move around. And so some will be more to one side than the other at any moment in time. So here's a summary of the intermolecular forces. Remember, London dispersion and dipole-dipole are types of van der Waals forces. It tells you nonpolar molecules are involved in London dispersion. Polar molecules can have London dispersion and dipole-dipole. And if those polar molecules have nitrogen, oxygen, or fluorine, they can have all three. So we've already talked about this, but some physical properties based on these intermolecular forces. The stronger the intermolecular force, the more energy that's needed to break them. So the higher the melting and the boiling point. Okay. There is an exception to this. These are called giant covalent structures. These are things that have covalent bonds and are nonpolar, but they have such a giant network structure in them, like diamond, all of the carbon atoms in diamond, that it causes them to have super, super high melting and boiling points. But if it's not a giant covalent structure, it's not going to have these really high melting and boiling points. It also explains again why many covalent substances are liquids and gases, because a lot of them are nonpolar or they have weak intermolecular forces. And again, how different the polarity is between atoms can determine the melting and boiling point as well, whereas the more difference in polarity, the higher the melting and boiling point will be. Okay, so the last thing I want to talk about is how these properties affect solubility, because that is a physical property that also depends on intermolecular forces. If two things have similar intermolecular forces, they will dissolve, and that's because like dissolves like. So if something is nonpolar and only contains London dispersion forces, it's going to dissolve in something else nonpolar. For example, in oils. So halogens, which are nonpolar, because they're fluorine, bromine, chlorine, iodine, they can dissolve in oil because oil is also nonpolar. Polar things are generally soluble in water, which is also highly polar, through the formation of both dipole-dipole and hydrogen bonds. So, for example, hydrogen chloride gas is soluble in things that are also polar, like water. Biological systems are also mostly containing polar covalent molecules because the body consists of mostly water, right? So, in order to dissolve these compounds, these biological systems are mostly polar covalent molecules, like DNA, like carbohydrates. An exception would be lipids, but again, lipids do have a polar component to it and also a nonpolar component. Okay, so if you have a larger molecule, whenever you have a small part of it that's polar, okay? So you could have, again, like a lipid, something that's both polar and nonpolar. If the nonpolar part is bigger, then it's not going to be that soluble in a polar solvent. Remember, solvent is the thing that does the dissolving. So for example, if you have something with 2 carbons versus something with 7 carbons, even though you might have hydrogen bonding in the smaller organic molecule, it's going to be much more soluble in water compared to the one with 7 carbons, because there's a really large portion of that molecule that's nonpolar. So yes, it's partially soluble in water, but it's because it's so much bigger, it's probably going to dissolve better in a more nonpolar solvent. So nonpolar things don't like to dissolve in water, again, because it's polar, and polar substances don't really dissolve in things that are nonpolar because they can't form intermolecular forces with the solvent because one is polar and one is not. Giant molecular substances generally don't like to dissolve in anything because too much energy is required to break the strong covalent bonds in their structure. So giant covalent things are kind of different because they form covalent bonds between all of the atoms in the structure. So like diamond, for example, is a big network of covalently bonded carbon atoms. There's not really intermolecular forces in it, it's more similar to ionic than covalent, if anything. So we've already talked about conductivity. So things that are covalent don't conduct electricity well in any state. That's because they don't contain ions. However, some polar covalent molecules can ionize in certain conditions and will conduct electricity. This mainly happens with acids. So if you have like hydrochloric acid, it does dissolve in water to form hydrogen and chloride ions. So in that case, they can conduct electricity. Normally, we said that covalent compounds can't really conduct electricity in water, but they can if they're really polar. And also, some giant covalent compounds can conduct electricity if their electrons are somewhat mobile. For example, graphite and graphene are electrical conductors just because the electrons in those giant covalent structures are somewhat mobile. Some also, like silicon, have semiconductive properties. So here is a summary of different physical properties of the types of compounds we have discussed. And here is a fun, well, I think it's fun, a fun practice problem for you guys to try in order to identify if something is ionic, nonpolar, polar molecular metal, or a giant molecular substance. So you guys can try that if you want to. All right, and that is it for today. Let me know if you guys have any questions, and I hope you have a great rest of your day. Bye.